All right, so 4.5 brings us into graphing exponential functions, and I know everybody's going to be very excited about this. 4.5 is just an introduction to the graphing, and then we'll get into transformations in 4.6, which is why I've kind of combined the two of them together. So with 4.5, we're just looking at exponential graphs. Now, normally I would have students use Desmos or some sort of graphing software to graph these, but based on the circumstances, I'll just go ahead and show you what these graphs would look like. So for the first one, we have y equals 2 to the exponent x. So this graph, if we were to graph it, it would kind of look something like this. Okay, kind of going up to the right. Now, one important aspect of an exponential function is that it crosses the y-axis at 1. And if we look through the characteristics of that, our domain, because it continues on indefinitely in both directions, the domain would be xer, right? Includes all x values. The range in this case is that my y's have to be greater than 0. So y greater than 0, yer. Now notice that y has to be greater than 0, but not equal to. And that's because if I put something in here for x as an exponent, I can never get this entire power to equal 0, right? Because 2 to the exponent of 0 would be 1. There's nothing I can do that can make this actually 0. And because of that, y has to be greater than 0, not equal to. Similarly, if I put a negative value in here for x, say 2 to the exponent negative 1, well, 2 to the exponent negative 1, we know is a half. 2 to the exponent negative 2 would be a quarter, meaning that as x becomes more negative, y is still going to be positive. It's just going to become a very small fraction. So in fact, I can never get my y value to be negative because there's no value that I can put in for x that can make this entire thing a negative value. So our line does not touch the x-axis, nor does it go below it. For intercepts, we only have one that occurs when y equals 1. And for asymptote, I just mentioned that because this line can't touch the x-axis, there's an asymptote that occurs at y equal to 0 because our line can't touch it or cross it. Increasing or decreasing, that just means that as you're going from the graph from left to right, what's happening? Well, my graph is going up. So it would be increasing. Now, if we look at the next graph, 5 to the exponent x, something similar occurs. It goes up to the right, like this. Still going in the same direction, still crosses the y-axis at 1. But one thing that is different is because the base is larger, right? I've gone from 2 to 5. Because the base is larger, my graph becomes much more steep. It's going to become much more vertical now as opposed to my 2 to the exponent x. And that makes sense, right? If x is 2, 2 to the exponent 2 is 4. So when x is 2, I'm going to be at 4. Whereas in this case, when x is 2, my y value is now going to be 25. So naturally, it's going to become much more steep. Aside from that, though, my domain is still xer. My range, y greater than 0. My y-intercept stays the same at y equals 1. Asymptote is still the same at y equals 0. And again, we're going in the same direction, so we're increasing. So even though the base changes from 2 to 5, the characteristics of the graph are still the same. The only change, of course, is that the graph becomes more steep. Now, what happens when the base becomes a fraction? Well, in this case, my graph is going to go in the opposite direction. And we still cross the y-axis at 1. So the domain is the same, XCR. The range is the same, y greater than 0, YER. Because again, if I put a negative value in for x, I can't make this y value negative. Intercepts, again, same spot at y equals 1. Asymptote is the same at y equals 0. The only change here is that because it's a fraction, what we notice is that we're actually going down to the right. So now this function is decreasing. And for our last graph, 1/5 the exponent x, again, same characteristics, still crossing at 1. The difference, much more steep of a decrease. 1/2, a bit more gradual. 1/5, much more steep. So the smaller the fraction, the steeper the decrease. The domain is still XCR. The range remains the same at y greater than 0. Same, and again, decreasing. So even though we change the base of our exponent, the graph's characteristics all remain the same, just becoming more or less steep or decreasing rather than increasing. And that's just an introduction into types of exponential graphs. So on the next page, we just kind of summarize that. So an exponential function where we have b to the exponent x, where b is the base, an increasing function represents growth when the base is greater than 1, and a decreasing function when our base is a fraction, meaning less than 1, but greater than 0. So if we want, we can say here that's growth when we're dealing with a whole number, and it's decay or decreasing when it's a fraction. And then the characteristics that we summarized at the previous table, if the base is greater than 0, so if it's a whole number, domain will be XCR, and the range is always y greater than 0, YER. If the base is greater than 1, so if it's a whole number, the larger the base, the steeper the graph. And if my base is a fraction, meaning between 0 and 1, the smaller the base, the steeper the graph. The function has the x-axis where y equals 0 as a horizontal asymptote. And all the graphs, we noticed, they all have a y-intercept of 1. So the reason why I went through that is just to show you what an exponential graph looks like. Dare I say, parent function of an exponential. And the reason why we go through that is because moving into 4.6, we're now dealing with transformations. So transformations take us back to really unit 1. And then we did some more, I guess it was just unit 1 with the transformations. So as a review, the 2, the number in front, that's our quote A value, vertical stretch compression. The 1/2 right in front of the x, where there's a bracket, The 1/2 is the k value. X plus 5, right, is the d value. And the -7 at the end is a c value. Now, everything here has been talked about except for this 3. And that's because the 3 is the base of my function. Because the exponent, 1/2 x plus 5, that exponent is attached to this base, right? It's up and to the right. So we use this base with this exponent to create our transformations. So as we work through our transformations here, we're going to start with the base, because the base gives us the parent function. So really, our parent function, or the original graph, is going to be fx equals 3 to the exponent x. Because this question has a base 3, so I'm going to use 3 to the exponent x as my parent before I apply any transformations. Now, with transformations, because exponentials can get either really, really large or really, really small, in order to graph them, you're dealing with massive numbers or you're dealing with very, very, very small decimals in some cases. So because of that, you can't really fit all of that onto a grid. So what we do is we just want to see what the behavior is like around the y-axis. That's really all we care about when we graph. So because of that, we are always, no matter what, looking at values from -1 to +1. So always look at those values. So 3 to the exponent -1 is 1/3. 3 to the exponent 0 is 1. And 3 to the exponent 1 is 3. And that's how we get our first 3 points from the parent function in order to apply our transformations. Once we have these, we're going to go through our transformations just like we did in Unit 1. So we start with the 2. The 2 is the a value. So the a value, which is 2, means that we need to multiply the y values by 2. Right? Because that's our vertical stretch. Vertical stretch means we multiply the y's by 2. The 3 is the base. We don't deal with that. We move to the 1/2. The 1/2 is the k value. And the k, we know, we multiply the x values by 2. Right? When it comes to the k value, you're multiplying by the reciprocal. So because the k value is 1/2, we multiply by 2. By the reciprocal. D value is 5. That means that we have a horizontal translation. Five units left. And the -7, which is the c value, is a vertical translation. Seven units down. So the a value, we know affects the y. K is x, d is x, and c is y. And again, if you remember from unit 1, kind of way back in February, it goes y, x, x, y. And in this case, it's easier to remember because anything in the exponents involve the x's. So exponent x, easy to remember. Now from unit 1, we did one of those massive tables, right? You had to do step by step by step, and it took us forever to fill in the table. We're not going to worry about the tables anymore because there was a faster, more effective way of doing this than with those tables. So we have two variables. We have the x and we have the y. So the a value is 2. That means we multiply our y's by 2. So I'm just going to do 2y, multiply my y value by 2. K value means I multiply the x's by 2. So I'm going to make that 2x, multiply my x's by 2. For d value, I'm going 5 units to the left. So I'm going to do minus 5, right? I'm doing the opposite of what's in my question. And then vertical translation 7 down, that subtracts from my y, minus 7. And what I've done now is I've created an expression to determine my new points. Rather than using the table, I can just create these two expressions to determine my new x and y values. So from my parent function, I have negative 1 and 1/3, 0, 1, and 1, 3. I'm going to take my x's, I'm going to sub them in here for x, and I'm going to get my new values. So I take these, I sub them in, and let's see what we get. If I take negative 1 and sub it in for x, I get 2 times negative 1, which is negative 2. Negative 2 minus 5, negative 7. Sub 0 in. 0 minus 5 is negative 5. Sub in 1. 2 times 1 is 2. Minus 5 gives me negative 3. Same thing with the y values. 1/3 I subbed in for y. So 2/3 minus 7 gives us negative 6 and 2/3. 2 times 1 is 2, minus 7 is negative 5. 2 times 3 is 6, minus 7 is negative 1. Now this gives us our transformed points. And these are what we're going to plot on our grid. So, negative 7, negative 6, and 2/3. So just about at negative 7. We'll put our point. Negative 5, negative 5, negative 5, negative 5, and then negative 3, negative 1. And we have our 3 points. So what we need to do now is just kind of connect those, and we're good. Except, remember from our parent functions, each of those graphs has an asymptote. So when we transform them, there's still going to be an asymptote present. And the asymptote is always the c value. So my c value is also the asymptote. So before we connect these 3 dots, what we want to do, just like before, is with a line, if you wish, go to negative 7. And you can put in a dashed line if you want, or a solid line. But we want to make sure that when we draw our graph, that we do not touch the asymptote. So once that's in place, Now it becomes much easier because we can go here, touch our points, and then from here it's just freehand, right? We don't know exactly where it goes. We just want to kind of follow that pattern. And there's our graph. So I'm just going to put a line here, our asymptote when y equals -7. Okay, and that's graphing exponentials. So we're only using those 3 points, -1, 0, and 1. We create our expressions, we sub them in, we get our new points, and we graph. So, let's look at our next example. First thing we need is the base, right? So in this case, the base is 1/3. So fx equals 1/3 to the exponent x is our parent function. From that, we always use -1, 0, and 1 to get our 3 points. Always. So 1/3 to the exponent -1 is 3. 1/3 to the exponent 0 is 1. And 1/3 to the exponent 1 is, of course, a third. Once we have our points, we now need to determine our expressions. So I'll put in the x and the y. The -2 is the a value, which means I multiply the y's by -2. I have a negative up here in front of the x, separated by a bracket, so k value. So the reciprocal of a -1 is still going to be a -1. So -x plus 1, do the opposite, -1. And then 2y plus 1. And that becomes my new expression. Take my x's, sub in for x. Take my y's, sub in for y. So I sub at -1 in for x. I get -1, but the negative of -1, which is +1, minus 1 is 0. -2 times 3 is -6, plus 1, -5. Do the same thing for the next one. Sub 0 in for x, sub 1 in for y. We end up with -1, -1. And for the last point, we get -2 and +1/3. So we have our points to plot. Before we do, last number, right, our c value, asymptote. And if you want to write that in before you plot your points or after, it doesn't matter. So 0, -5, -1, -1, -2, and then +1/3. And the asymptote, of course, is at +1. Of course, if you go to graph and your points go across the asymptote, you know you've made a mistake someplace, because that can never, ever happen. Now, what this looks like, since we can't cross the asymptote, is this going to look pretty much like a 90-degree angle. All right, we're coming in here, hitting this point, and then almost going straight down. We're going to have a sharp turn there. So you notice that now we're going in this direction because, based on the transformations, this -2 implies we have a reflection in the x-axis. And then this negative here is a reflection in the y. So we have a couple reflections happening, which is why it's down here in this direction. Just like in Unit 1, keep in mind that the k value and the x must be separated by a bracket, right? So here, we need a bracket. And if you don't have one, that's an indication that you're required to factor. So this then becomes 4 exponent negative 3 bracket x minus 3 and then plus 2. We want a common factor that negative 3 out so there's a bracket between the negative 3 and the x. In this case, our base is 4. So I'll just put here dx equals 4 to the exponent x. We use our points, negative 1, 0, and 1. 4 to the exponent negative 1 is a quarter. 4 to the exponent 0 is 1. And 4 to the exponent 1 is 4. Our expressions for x and y. I don't have a value here. I have a k value of negative 3, which means I'm multiplying x by negative 1/3 and adding 3, right? X exponents. So this here will deal with the x. And the y, I'm just simply adding 2. I sub my values in again.